Here's another basic stoichiometry problem. On your quiz, you will have a combustion problem. And so if I burn 10 grams of butane, well, 10.0, three significant figures is the important point there, of butane, what is the mass of water produced? Hopefully when we look at that right off, we go, I need a balanced chemical equation. I guess one question is, what is butane? I would give that to you, but butane is a 4-carbon chain. It is a completely saturated 4-carbon chain, so it's a carbon bound to a carbon, bound to a carbon, bound to a carbon. Each carbon is saturated in hydrogens. Of course, I can draw it like this, and that would give me an accurate representation of how many atoms are on each. These would each be tetrahedral centers, and so the real bond angles would always be 109, and we've covered some of these things. This would not lay flat. It would be a three-dimensional structure, and I can't draw that here. But what it does get right is that there is 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And we're going to need to know that to balance the chemical equation. Of course, eventually we'll need to know the mass of that molecule. C4H10. Notice I've left a little space before it. I'm going to leave a little space. I need O2, oxygen, in order to burn anything. This is a reaction that's going to take place to produce water. I'm going to leave a space again so that I can write a number there. And again, leave a space. It's going to also produce carbon dioxide. We recognize some things right off is that there's 2 places there are carbons and only 2 places there are carbons, and there's 2 places there are hydrogens and only 2 places there are hydrogens, but then there's 3 places there are oxygens, and so it's important to do the oxygens last is what I would say. The other thing to notice is the oxygens on this side only come in pairs. So no matter what, over here I'm going to need an even number of oxygens. And feel free to give some trial and error. If there is going to be an odd number of oxygens, the odd number is going to come from here, because no matter how many carbon dioxides I have, it's always going to be an even number. When I look over here, butane has 10 hydrogens. Water has 2 hydrogens. So to make these match, if I have one of these, one butane molecule, I need 5 water molecules. There's a problem. If I have 5 water molecules, I'm going to have 5 oxygens. That's an odd number, so no matter how many of these, it's not going to match. So with a little deductive reasoning, I get to realize I need a 2 here. And then I have a total of 20 hydrogen atoms in 2 butanes, and that means that I will need 10 water molecules. There's 4 carbons in each butane. I have 2. I'm going to need 8 carbon dioxide molecules. And now the carbons and the hydrogens are balanced. I just need to finish with the oxygens. There's 16 oxygens there. And here is 10 more. And so that's 26. And so oxygen only comes in pairs. And so I need 13. And there's a balanced chemical reaction. I would say, certainly on a quiz or a test, I would add states of matter. Butane is what is found in lighters, and it's a liquid in your lighter, but when you push the button, the gas comes out, right? And the gas is what burns. Liquids generally don't burn. It's the vapors of the liquids that burn, right? You've seen me pour methanol on a countertop and light it on fire, it doesn't just all disappear. In fact, I can blow it out and the liquid's still there, and I can light it again because it's the vapors, the evaporating liquid, which is burning, not the liquid itself. Oxygen is almost always a gas except for in extreme conditions. The water that is produced in fire is a gas. Of course, we can cool it down and turn it into a liquid. And carbon dioxide is also almost always a gas except for in extreme conditions. I think it's reasonable to put a delta there. That delta would be the delta saying that this stuff is not going to become that stuff unless that happens. So that's my spark or my lighter or whatever ignites the fire. I would also say that that delta makes this reaction safe, meaning that butane isn't going to react with oxygen unless I light it on fire. But if I do light it on fire, it will burn. And so that's the heat produced in the reaction. The reason that we put butane in a lighter is because once we add a spark, it does burn. So this is the one I say makes it dangerous, because if it does get lit on fire, it can burn. All right. So we got a lot done there. I would say, just thinking ahead, the other thing we know we need is the mass of this molecule. It's 4 carbons, and carbons are, I'm going to round because I have 3 significant figures there. And if I look at my periodic table, carbon to 3 significant figures is 12.0. So I'll say 12.0. And that has units of grams of carbon per mole of carbon. And then I would have 10 hydrogens. And again, hydrogen 1.01. When I add the ones, I'm going to put 1.0, and there's a reason that actually doesn't mess up my significant figures, because we're going to be adding in a second. And that is grams, oh, I guess I will put the 1 there. It's not going to quite go away. Grams of hydrogen per mole of hydrogen, because that's a 10, which is going to move the decimal. If you mess those kind of things up on these quizzes and tests, it's not such a big deal. That's 48. That is 10.1. So this should be 58.1 grams of butane. I'm just going to write BU for butane, per mole of butane. And now we need to look. The only information we're given in this is that we started with 10 grams of butane. I'm going to put that 10.0 grams of butane divided by 1. Nothing in chemistry happens in grams. Everything happens in moles. We can't measure moles. We have to measure grams. But I have to get rid of those grams of butane, and I have to replace them with moles of butane. That was the point that we just went through there to get this 58.1 grams per mole. And so, again, it's 58.1 grams per 1 mole. And now grams of butane are going away. The question asks for, what is the mass of water? So I need to get rid of butane and get water back. That's what the balanced chemical reaction does. For every 2 moles of butane burned, I'm going to get 10 moles of water. So I need to get rid, again, just reflex. Moles of butane are going on the bottom. It's asking for moles of water. And again, the ratio is 2 moles of butane produce 10 moles of water. Again, I can't measure moles of water. So what I can do is weigh the mass of water. I mean, this is a common. I could condense the water, burn through a cooled tube, and collect the water, so on and so forth. So I need to get rid of moles of water, because that's not usable, and keep grams of water. And it's 18.0 grams per 1 mole. Do the math similar to this: 1 oxygen, 2 hydrogens to 3 sig figs. Oh, sorry, I don't need to do anything after that. And then I just need an equal sign, noticing units cancel. Grams of butane cancel. Grams of butane, moles with moles of butane, moles of water with moles of water. I'm going to get grams of water. 10.0 times 10. Notice that these numbers have infinite number of significant figures. It's really 10.0000000 moles of water for every 2.0000000 moles of butane forever and ever. So that's never going to limit your number of sig figs in your answer. Times 18 divided by everything on the bottom, 58.1 times 2. And again, don't forget units, grams of H2O. And we just put that in the calculator. clear 10 times 10 times 18 divided by 58.1 times, oops, I need to go back, that shouldn't be times, that should be divided by 2. I could use parentheses, but I'm telling you that's how that works. And I would get 15.5 grams of water. And I've asked this question before, and I'll ask it again. Does this answer make sense? Believe it or not, that's a 5. And the answer is yes. All right, we started off with 10 grams of butane, and we got 15 grams of water. It's more water than butane that we started with. But if we look at our chemical reaction, this reaction is a whole lot of oxygen from the air. So the butane is mixing with the oxygen from the air to produce water and carbon dioxide. The total mass of the stuff over here has to equal the total mass of the stuff over here. The mass of the butane does not have to equal the mass of the water. So it makes perfect sense that we ended up with more mass in water than we did in butane that we started with.